I'm going to present QUARTET quantitative robotic specification patterns. If you go into our website, you will see our pattern catalog with a list of all the elementary patterns, composite patterns, and other information available. The DSL, how we describe them in our tool, and the tool itself that can be downloaded from GitHub. I already downloaded from the GitHub repository the code and loaded it into Eclipse IDE, and this is how it looks. We can see the eCore file, and this file contains all the descriptions that are related to the DSL. So let's go and run the .myDSL as an Eclipse application. This contains two files. One is example1 with 3 different missions. I'm going to explain how we describe them in a minute. And the second file is QUARTET examples with a list of multiple missions inside the problem specifications with different locations, robots, and conditions. Let's start with an example to see how QUARTET works. I'm going to create a new file with a name that describes that a robot reached a location done. I need to call it myDSL.myDSL so that it is compiled following the rules of our DSL. Let's create the problem specifications. We start with a location. Let's call this location goal. Let's create a robot. I'm going to call it R1 pick and place. And the mission with an ID M1. And I want to minimize the traveling cost of R1, my robot. Visiting, shall visit, and the name of the location, which is go. Okay, so let's clean this project and save it. And in the folder called srcgen, we can see a new file with the specification described. This specification is written in Prism. Let's open Prism and we can add our property. There's an error that says that it's not declared, and it's because we haven't created a model, but that's fine for now. Let's go and create a small model. We must define the necessary labels. In this case, I have one label, which is R1 pick and place goal, defined as a state where the robot is done. So when the robot reaches done, that means the robot has arrived to the goal. Create modules in Prism to define variables and transitions. So let's put this R1 done inside the module of robot R1. This is going to be a Boolean variable and it's going to start in false. I can create some transitions as well. Oh, I need to define the model as an MDP. I'm going to choose an MDP because I'm working with minimizing probabilities, and this is a type of model that can handle these properties. Let's define a variable that is called robot1 start, where the robot is ready to go. So we say that the robot transitions from a state where it is ready to go to done. And other possible states that can be reached. Before that, let's state that the probability of transitioning to state done is P, and let's define this P as a constant, and let's say with a big probability, 0.9, this robot completes the mission, it arrives to the goal. And with probability 1 minus P, it doesn't. So this is false. We can just leave it with one transition. And also this needs to be double. Okay, so now we can check our property, we verify it, and it says that the minimum probability of reaching a goal is 1. Let's add an update so that the robot cannot eventually reach this state of done. If I add that the robot after one transition cannot restart, the robot won't be able to reach it with probability 1. Check this property again, and the verification result says 0.1. Just 0.1 of the times will reach the state done. Okay, so let's do another very simple example, the same as M1, but in this case, instead of minimizing, I want to maximize. Let's save this file and check the generated property. Take this into Prism. And verify. Okay, so in this case, the minimum probability and the maximum probability is 0.9. That is because of the model, the description of the model. So let's make it again a bit more interesting and make another transition. In this case, the robot can reach the state R1 done with a probability of Q. And the probability Q is going to be set to 0.7. So in this case, there are two ways of reaching the state done, one with P probability, the other one with Q probability. And if we check our formulas again, we will see 0.7 and 0.9 as minimum and max probabilities. Okay, so those were two examples. Let's go quickly to a third one where robot 1 shall react instantly to some condition. I want this condition to be when the battery is low and avoiding allocation, CP. Okay, so let's save it and copy the CTL formula generated into Prism. We repeat the same procedure. Create the necessary labels, C1 and R1CP. We verified our formula and we get some result. In this case, that it is true. We have verified 3 simple formulae generated by QUARTET. There are also 2 files. One is example 1 with 3 different missions. If we save this file, we're going to see the 3 corresponding solutions. The first one says warning, translation into Prism not supported, and it gives some feedback into why this formula is not supported. For the second and third missions, the formulas are generated. If you see the third one, for instance, it's difficult to come up with this one by hand. Hence, the necessity of writing specifications in QUARTET.